Okay, problem 3. Which of the following series converge and which diverge? Find the sum if the series is convergent. Okay, find the sum if the series is convergent. Right. So before that, we're going to talk about a divergent test. The divergent test. Okay, what is a divergent test? So if the sequence limit is not 0, okay, then the series must be divergent. Okay, if a sequence limit is not 0, then the series must be divergent. This is very useful when we want to know whether a series is divergent or convergent. Okay, for example, in part A, okay, we want to know whether this series, whether this infinite sum is convergent or divergent. So what we can do, right? First, we can find out the limit of its sequence. Okay, so remember, series is an infinite sum. Sequence is just a row of values. So let's just find the limit of its sequence. Okay, the top, it's a polynomial. Let's open it. It's n squared plus n over n squared plus 5n plus 6. Okay, so what can we do here? We can do substitution, but it's infinity over infinity. So we can divide both sides by n to the highest power, which is n squared here. Right, so it's 1 plus 1 over n, and the bottom is 1 plus 5 over n plus 6 over n squared. Okay, then when n is approaching infinity, it's 0, and so it's 1 over 1. The result is 1. Okay, so the limit of the sequence is not 0. Okay, the limit of the sequence is not 0, so by the divergent test, the series must be divergent. Okay, so you can quickly conclude that this series is divergent. Okay, and one question, is the sequence convergent? Yes, because the sequence is convergent because you get its limit, it's 1, right? It's a constant number. It's a constant. So the sequence is convergent. But because the sequence limit is not 0, so the series must be divergent. Okay? And another common question, what if, right? What if you calculate this limit? What if it's 0? Okay, can we make any conclusion? What if you calculate the limit and you get the result? It is 0. Okay, if it is 0, no conclusion. Okay, if it is 0, no conclusion. So let me write it down here. If the limit is 0, okay, no conclusion. Because if it is 0, the series could be convergent, it could be divergent. So what should you do now? You should apply other methods you've learned. Okay, you should apply other methods you've learned. So we wish the limit is not 0, right? Because in that case, we can straightforward conclude that it is divergent. But if it is 0, then we can't make any conclusion. We have to use other methods. Second one, n from 1 to infinity. E to the power of n over e to the power of n plus n. Okay, again, we want to know the series is convergent or divergent. We can first figure out the limit of its sequence. Okay, how do you get the limit of the sequence here? How do you get the limit of the sequence here? First, let's try substitution. It's going to be infinity over infinity. So we want to use the L'Hopital rule. Okay, again, if we want to use the L'Hopital rule, we need to change the sequence to a continuous function because technically you can only apply L'Hopital rule to a continuous function. Okay, then because both the top and the bottom, they're approaching infinity, so we can apply the Lobtus rule. So it's the limit x approaching infinity. The top is e to the power of x. The bottom is e to the power of x plus 1. Okay, then when x is approaching infinity, this is 0. Sorry, it's still infinity over infinity, right? So you need to apply Lobtus rule again. The top, the derivative of e to the power of x is itself. The bottom, the derivative of e to the power of x plus 1 is e to the power of x. Now, the top and the bottom, they are canceled out, right? So the result is 1. Again, the result is 1. That means the sequence is convergent, right? Because you get the limit, it's 1, it's a constant, so the sequence is convergent. But for the series, right, by the divergence test, if the sequence limit is not 0, then the series must be divergent. Okay, then the series must be divergent. That's part B. Okay, part C, we have n from 1 to infinity cosine n pi. Okay, so here, let's write down the first few terms. It's when n is 1, it's cosine pi, right? When n is 2, okay, let me write it down here. When n is 1, it is cosine pi. When n is 2, it is 2 pi. N is 3, it is 3 pi, etc., etc., right? So, what is cosine pi? Cosine pi is negative 1. Cosine 2 pi, positive 1. Cosine 3 pi, negative 1. Right, so you can see it is actually a positive plus minus 1 disguised in the cosine form, right? Essentially, it is minus 1 plus 1 minus 1 plus 1. So you can rewrite it as negative 1 to the power of n. Okay, it's just negative 1 to the power of 1. This is just negative 1 to the power of 2. It's negative 1 to the power of 3. It is negative 1 to the power of 4. Which means this cosine n pi, it is essentially equivalent to negative 1 to the power of n, right? These are two equivalent stuff. So we can change it to the sum, right? Negative 1 to the power of n, which is much clearer here because it's going to be minus 1 plus 1 minus 1, sorry, minus 1 plus 1 minus 1 plus 1, etc., right? So it is clearly divergent. You don't even have to, you don't even have to apply any like divergent test or anything. You can straightforward conclude it is divergent. Okay, part D, it is cosine n pi over 5 to the power of n. Okay, it is cosine n pi over 5 to the power of n. So the first part, cosine n pi, it is negative 1 to the power of n over 5 to the power of n, right? So just now we've proved cosine n pi is equivalent to negative 1 to the power of n. So it is very clear, right? It is a geometric series. Just a quick review, a geometric series, it looks like this. Okay, let me do it here. The geometric series, it is a times r to the power of n. The geometric series, the details are covered in problem 2. If you missed that, you can go back. So here, just a quick review. It is convergent if the absolute value of r is smaller than 1. It is divergent if the absolute value of r is greater or equal to 1. And if it's convergent, then what is the sum? Okay, then what is the sum? Okay, if it's from 0 to infinity and it's convergent, then the sum is a over 1 minus r. Okay, if it is from 1 to infinity, the sum is ar over 1 minus r. Again, the derivation is covered in problem 2. Just go there and check. Okay, and clearly here, this is a geometric series, right? A is 1, right? So A is 1. Actually, this is R. So it is convergent, right? So since the absolute is convergent, okay, is convergent. Since it's a geometric series and its absolute value of ratio, which is -1/5 here, is smaller than 1. Okay, then what is the result? Right, so it is from 1 to infinity, so we need to do this. It is a times r over 1 minus r. Right, so it is -1/6. Wait. Yeah, it is -1/6. Okay, so similarly, we can do problems F and G first. F is, okay, 2 over to the power of n plus 3 to the power of n over 5 to the power of n. Okay, so first we can split it into two different geometric series. Right, so this is the first part, 2 over 5 to the power of n. And then the second part, it is 3 over 5 to the power of n. And both geometric series, they are pretty clear, right? The ratio r is smaller than 1. So they're both convergent. So the sum is also convergent. Right? So it is convergent. Okay, because it's a geometric series, right? Because both are geometric series and both ratios are, absolute values are smaller than 1. Okay, then let's just follow this formula to write down its sum. It's AR, A is 1 times R over 1 minus R. This is 1 times R over 1 minus R. Okay, and just finish your calculation. And just finish your calculation, and you'll get the answer, which is 13/6. Right. What about part G? Part G, okay, it looks a little bit complicated, but actually it's not. It's e to the power of, it is e to the power of n pi over pi to the power of ne. Okay, it looks like it has a lot of variables, but actually e and pi, they are both constants. Right? They're just special constants, so we have to use letters to represent them. Essentially, it's just e to the power of pi over pi to the power of e to the power of n. Right? This top is e to the power of n pi. This bottom, right, to the power of n is e to the power of n pi to the power of n e. Okay, so we just need to use our calculator to get the value of this. Right? To get the value of this. So e is a number which is around 2.7, pi is like 3.14 or something, and over 3.14 to the power of 2.7. Okay, so this ratio is, right, it is divergent. Since it's a geometric series and the ratio, the absolute value of its ratio, it is greater than 1. Okay, since the absolute value of its ratio is greater than 1. All right. So the last question, it is about E, right? Part E, it's the series, right? What is a series? It's for n from 1 to infinity, lowering 1 over 3 to the power of n. Okay, lowering 1 over 3 to the power of n. So again, let's use a divergent test. Let's just figure out the limit of the sequence. So as you can see, when n is approaching infinity, this 3 to the power of n is approaching infinity. Right, so it's 1 over infinity, it's going to be 0. Right, so lowering 0 is going to be approaching negative infinity. Right, so the result is 0, negative infinity. So the limit of the sequence is not 0, right, clearly. So by divergent test, this series is divergent. Okay, this series is divergent. So in this question, we've used For some questions, we use divergence test. For other questions, they are geometric series. So we just just check whether R is absolute value is smaller than 1 or greater or equal to. Okay.